Here we go with another video on geometry. I've made a lot of these in the last 15 years. They're never scripted and I never worry about the background or anything. Mostly I just ramble. So here's another one. I think most guys, most modelers, that they think their geometry is good, or they don't really care about their geometry. It works, or worked in the past the same way, so why bother changing it? And one of the biggest ways that I've proven this, and proven that they might should pay more attention to their geometry, is with the rudder. It's easy to show, and I've never had a case where I wasn't able to show it on any beautiful custom giant scale plane. Just every single one, every time, no matter how nice it is and how sharp the guy is. If you pick up the rudder, pick up the the ass end of the plane, and if you fully open the rudder, it will shut itself every time. I've never seen anybody have a plane that didn't. Their geometry on their tail wheel is not set up right, and when they're in the air, they get decent ground handling. They think they have good ground, I mean, they have good ground handling, not as good as they think they have it, as good as they could have it, but they don't. This ground handling is going to be better. But in the air, when I have my rudder deflected and the wind's blowing on it, this servo is only, this set of servos is only holding against the wind and the prop blast. It's not pulling these springs down here at the same time. Everybody's plane I've seen that has springs, the direct drive's not as bad, but everybody who has a hay style shape like this and springs, everyone I've ever seen, they're all set up to pull. So they're non-pulling spring. The inside one's pulling, the outside one's non-pulling. It has tension, so it's trying to pull the rudder back the whole time. So you're dealing with that. Your servos are dealing with it, and your batteries are dealing with it. And that's a good indicator that guys are really not thinking right about geometry. Then you take that over to the wings with gang servos, and then you wonder what's going on. Lots of things. In the same way that you can very easily prove that a guy is having his springs pulling on his rudder while he's trying to use his rudder for a maneuver, and he's wearing out his batteries and his servos more than he needs to. It's easy to prove it on the ailerons, but it does take actually looking at it more, because they don't just spring back. I told you I was going to ramble. Okay, so here we go. Let's start with how you could do it the way that some guys say you can. They say you just run the servo arm 90 degrees of the servo body, and you're going to be good. I know how to set planes up. I can drill them in the right places. I can do what I need to do. Yeah, there's two things I want to say about that. One is, in order for that to happen, you have to have your servo body, the side of your servo, perfectly perpendicular with the aileron. In this case, these are ailerons. Aileron hinge line. In this case, and a guy could do that. In this case, they're not. Because they're perpendicular to the trailing edge here, or the leading edge of the aileron, trailing edge of the wing, and this hinge line is at an angle to that leading and trailing edge. The hinge line here is very close, and here it's very far away. So that's going to be more challenging here. You still could do it. You still could mark that hinge line, and then you could set the servo body perpendicular to that. That's one. Then your pivot point for your ball joint needs to be directly over the hinge line. Very tricky to find a hinge line here after the fact, but on a normal beveled plane, this is pocket style, more scale, real cool. On a normal bevel style, you can see the hinge line, so you could find it. So if you get it, your pivot point directly over the hinge line, perfectly over it, and your servo body is exactly 90 degrees to that pivot point line, that hinge line, then you can put your servo arm 90 degrees to your servo body. And your geometry is probably going to be perfect too, but probably not. It's probably just be very close. And that's the second point I want to make. One of the downsides of doing that is, or maybe the only real downside to doing that, is all the planes I've set up that way, and you can see it on the rudder servo horns that some company makes. Some of the companies make these U-shaped in the hinge line rudder control horns, and you won't get much deflection. It'll hit the side of the fuse. And the same thing when you get your pivot point in the hinge line, you'll get about 40 degrees or so, and then that control horn will hit the surface. And you could work that out. You could make a detent, pocket in the wing, for that thing to hit. But you also got the ball joint going down there. You got your difference in geometry. You get into pry loads on your servo arm to servo connection. I talk about that in other videos. We want side load, not pry load. But you could try to work something out with that. I've always believed in I've always seen that a little bit of offset, like 3/8 offset from the hinge line to the pivot point, gets me more travel, keeping all the other parts of the geometry the way that I want them, keeping all my leverage is what I'm trying to get at. So I get more throw and I get better leverage and less pry load, servo arm to servo body. So those are good things to me. But a guy could take and have his arm 90 degrees servo body. He's just probably ended up with 40 degrees throw max. And that's not working these days on a lot of stuff, especially when you try the new, for me it's new because I've been out of it for a while, the new XFC style, freestyle maneuvers. They just require a lot of throw for all the braking that they do with the plane. So yeah, you can take and make those guys right that say it can be 90 degrees, I can do it. To the servo arm to the servo body 90 degrees, I can make it happen. Yes, you can, to an extent, but if you want to be sure that you actually did make it happen, put on a protractor. Make sure that the center of the protractor is your pivot point, your pin, your screw that goes through here, and that you're 90 degrees or parallel to the servo body, with your protractor. And once you have that set up and you have all your true 90s like we talked about, you're right over the hinge line and you're perpendicular to the accurate hinge line, go ahead and put it on a protractor, put it at 0, and then move your surface, measure, pull it up, let's say 5 inches, depending on the size of the plane and how much throw you have. Exactly 5. Now measure this perfectly with a ruler, exactly 5 inches. Find the same points, make sure you're 5. Mark that on the protractor. Let's say that turns out to be 50 degrees in your perfect setup of all 90s and all in line with the hinge line. And then put it down 5 inches, measure that with a ruler till it's exactly 5 inches, and make a mark on your protractor here. I'm going to bet you a lot of money that they won't be 90 and then exactly 50 over and exactly 40, whatever the case may be. They're going to be a little bit different. One's going to be 42, 44, something like that. The other one's going to be 40. They won't be exactly the same, most likely, owing to so many little variances that you can end up with. So even in a perfect world, even when trying to have a perfect world, which again is limited throw, blah blah blah, lack of leverage, you're not going to do it. It's very unlikely. You might hit 1 or 2, but most of your plane's not going to have them. So the nice thing is there's a way to adjust that. Even if you want to set it up that way, you can still use the protractor to fine tune it and actually get it perfectly straight, perfectly equal in distance. Why do we want it perfectly equal in distance? That may be the starting point that I should have had. But imagine if I set this particular servo up the way I want. I got the control horn height that I want for leverage. Now leverage, when I'm at full deflection this way, there's some things I want. One, and this is slightly more, but the hinge, the way Airworks has it on this, because they use different control horns, this control horn would have to go through the hinge to get what I wanted, and not much balsa, so I moved it to the side of the hinge. But I'm looking for, at max deflection, I'm looking for more of a straight parallel to the servo body angle here, just a little bit more angle than that, so that I have some angle here. What you don't want is when these get more lined up straight. Then you just have total pry load. You also have the possibility for this servo to bounce over to the other side and then get stuck and have the other aileron push it back and, you know, break, stall out the aileron and have you spin in. So you want some angle right here. I would even take, like, at full deflection, I like more of that angle. So I like the control horn just slightly over. This plane made that tough. But I can live with this. Then you're also looking on the side. You know, on the side here, you're looking for it to be parallel, not dipping way down or dipping way up to where you, again, have the wrong leverage going into the servo arm and the servo body. So that's some of the stuff you're looking for. And so you're looking for those parts for leverage. Then let's say you set it up the way you want. You got all your leverage right. You got your correct, there's two things that we're talking about here first, leverage and mechanical advantage. So you have your control horn height and your servo arm length at the point where you have the mechanical advantage that you're looking for, and then you have your other angles set to where you have the leverage points that you're looking for, and you say this is good. This is the point I'm trying to get to. So you say that's what you want. Now you measure 5 inches up each way, and you notice that you're 40 degrees one way here and 50 degrees the other. Well, even if this is the only servo, you don't want that. That means it's going quicker one way than the other way. And if you do it the same way in the opposite wing, then it's the opposite, and one's going quick, slow, one's going slow, quick. So throughout the range of travel, they're going at different times and speeds, different rates. So how do you end up axial with that? And that's when, you know, the really good guys set up the radios with lots of conditions and lots of differential. But if you have them going at the same time and rate on each side of the plane, then it's a much better starting point to start dialing your plane in. So how do we adjust the degrees at that point? We've got 5 inches up and down that we've set our linkages up for, but we're going 40 degrees one way and we're going 50 degrees the other. That happens just by adjusting the length of your push ride. That's what I always call this the to be determined center. So whether it's all set up for 90s, which is, you know, requires some accuracy, or it's set up for offset like I have to where I get more throw and better leverage, then better leverage angles, then all I do is adjust the length of the push rod. And I adjust it kind of randomly, you know, until I get closer and closer, and all of a sudden this new center point, center or neutral point, for that 5 inches up and down deflection gets me exactly, let's say, 50 degrees each way. In this particular plane, I'll let you know I have 55 degrees each way, gets me 55 degrees up and down on the throw meter. And that's how this plane worked out for full deflection. So I adjust the length of the push rod until whatever center this turns out to be, I have to travel 55 to go the same measured 5 inches and 55 to go the same measured 5 inches. So that's all a lot of scenery. So to get to the point I'm trying to make. So now you have this one done that way and you're satisfied. You like that one. That's how you would have it. Well, now you got to synchronize this one up with it. That has to be synchronized up. So you put this one together, and there's all kinds of variables on how this is going to work out. But the protractor will always get you to end up in the right place. The first thing you notice when you set this one up, similar to that one, is the same situation where you're getting a different amount of travel. To have to a measured 5 inches and a measured 5 inches very accurately, you're getting a different amount of travel. So you adjust the push rod until it's the same travel, but invariably it'll be a different travel than that travel, owing to the control horn heights, because you have a different thickness of the aileron and wing. So you might find that here, you know, you're traveling 40 degrees each way to get that 5 inches up and down, but here you were going 55 degrees each way. So all you do is you adjust the height of the control horn. Now, everybody knows you can measure from the hinge line. Now in this case, it's pretty impossible to measure from the hinge line. But if you have a plane where it's easier to measure from the hinge line, you can try that, and that will get you very close, or at least close. But again, the protractor will let you know exactly where you're at. You can think you have it. You might measure 1 3/4 inches off of both hinges to the pivot point. But you see, if that protractor says 55-55 and this one says 50-50, at that point that you've already done that measuring, it's letting you know that that's not completely accurate. So you just keep adjusting the height, of the control horns until this one is also 55-55, exact for that one, matching that one 55-55. And they're both getting exactly 5 inches up and down. Then you know that they're synchronized. At any point throughout the range of travel, they're both going to make the aileron go up the exact same distance. At any point throughout the range of travel, you could pop the arm off and there's no tension. You could just pop the arm off back and forth, put it on, take it off, put it on, take it off at any point throughout the range. Now, if you then you make a note of that and you say, 55 degrees each way off of this determined center, it's getting me exactly 5 inches on each way up and down from center on the aileron on this wing, and you match that on the other. You made a note, so on the other wing, you set it up similar, or the same basically, and then you start fine-tuning it, and you get to the point on the other wing where 55 degrees off a determined center in each direction gets you exactly that same measured 5 inches of deflection in each direction out here. Then you know that not only are all 4 of your servos, in this case 2 on each wing, 4, are synchronized and not fighting each other at any point throughout the range of travel, but you also know that when this goes up exactly an inch or exactly 2 or exactly 2 1/4 or 4 1/4, wherever this one's at, the other one has moved the exact same distance the opposite direction. If this is up, the other one goes down. If this is up 2 7/16, then the other one will be down 2 7/16. The IMAC guys are going to really appreciate that. But everybody can feel it too. Everybody can feel a good plane. You get a dial plane, you hand it to one of your friends, they know it's dialed, they know it's easier to fly. So then at that point you have a plane that you still may have to work out some trim. If you're really, invitational Tucson shootout pilot, those guys really work their planes over and do a lot of tuning, a lot of trimming, a lot of conditions, a lot of radio work. But it'll be very minimal and it'll be very easy to work with. You know what you got. Most of the rest of us guys like me, once I'm that axial, I pretty much all my planes set up this way for years and years. I pull up on an upline, pin the aileron, and I have axial rolls. To me, if I was, I always think of Jason Schulman, even though not everybody might, all the young kids might know who he is, but he had so many fine-tuned conditions and really tuned his planes. He could probably tell a little difference, and he put in a slight bit of differential one way or another, and make it even more perfect for him. But you get the idea. What you want is synchronized servos, and you want them to travel the same number of degrees on their swinging arc to make the surface go the same number of degrees or an inch or millimeter measurement, up and down, and have the opposite wing doing the exact same thing too. Obviously that's going to be better. So yeah, this takes another half hour to show somebody, whereas a rudder, I could show them instantly that, that they turn off your plane, lift up your tail, push your rudder all the way over, release it, it'll spring back, because their geometry is wrong on their tail wheel. So their outside spring is pulling all the time on the rudder. That doesn't seem good to me. This I actually have to, get a plane on the bench for them, or crawl under their plane, loosen up a screw, have them put the plane at half travel, and take that screw out and try to pop their arm off, and they'll see that it's probably can't do it. It's binding. Of course, you have your 5 and 7 point, spots on your radio. If a guy takes the time, he can really try to iron it out. You may even hit one of those spots when you go to pull it off. But if you go to every degree around there, you'll find that all the other spots are not hitting perfectly, and that they're going to be binding. Yeah, and even with those 7 point adjustments, it won't be exactly 3 inches up here to be 3 inches down over there, you know, in a mid-range of 5 inches. There's going to be all kinds of spots, no matter what you do with your radio. You can go forever with your radio and all your points and do whatever you want, and you're still not going to be perfectly synchronized both sides of the plane at any given point of travel. You know, this is the only way I know to do that. And yeah, so that's what you end up with. That's why I do that. You can, yeah, if you took the time with anybody else's plane to take that screw out and pop it off at every point in the travel, you'll see that they're not like that. And you know, it's not that hard. So the protractors, you know, I just go to Google, search protractor, get it, print it, scale it, cut out for the servo, and it's really easy to do. Your determined center is really easy to find. Adjusting your push rod length where you get the same degrees is easy. Adjusting your control horn height to where both have the same amount of degrees is easy. Measuring a distance, in this case 5, let's say 5 inches up and down, is easy. It's not like I'm saying you got to do something that's complicated or even that time consuming to end up with what I think is about the best result that we can get, on these models. Sorry about the ramble. That's what I do. Okay. Joe out.